If you've ever seen any of my videos where we talk about amplitude, you know that 70% of the power is lost from the time it leaves the mainspring and travels through the powertrain to the escapement due to friction. Today, I'm going to show you how to get some of it back. If you're going to be working on vintage pocket watches like our Hamilton 917 project, here are 4 more things that you need to make sure of. The first part of the train inspection should be checking to make sure that the end and side shake are correct and that there's no binding in the train. In jeweled trains, side shake is typically not going to be an issue unless the pivot has been broken. What would be more typical is the end shake is incorrect because one of the jewels has been set incorrectly or it's been moved by accident. One of the more common issues is when there's a center second sweep. Oftentimes an inexperienced watchmaker will press on the 4th wheel pivot so hard when they're trying to install the second hand that the pivot on the other side of the 4th wheel pushes on the bridge jewel, changing its position, which creates too much end shake. Since the teeth of the 4th wheel mesh with the pinion of the escape wheel, it is operating at a lower torque because of the frictional loss of power as it's moving through the different wheels of the train. This can result in issues such as reduced or irregular amplitude readings on the time grapher, or even the complete stoppage of the movement. The only way to fix the end shake will be with a jeweling set. The second point of inspection is that the wheels in the pinions mesh together without any additional friction caused by either corrosion or damaged teeth. The teeth on the wheels and pinion leaves are shaped and designed in a way so that they can roll through each other with the minimum amount of friction. This type of friction was accounted for by the manufacturer when the movement was designed so that they know what size mainspring is required in order to have acceptable amplitude. Spend the time during your disassembly to inspect every wheel as you remove it and look for broken and damaged teeth on the brass wheels and for corrosion or rust on the steel pinions. If you find a wheel with broken or severely worn teeth, just look for a replacement wheel for now. When you're looking at the steel pinion leaves, you're typically not going to see one that's broken or worn because the brass teeth are softer than steel. But because they are made of steel and so old, you're typically going to see some corrosion. Any corrosion in the pinions is going to add friction as the teeth from one wheel turn the pinions on the next wheel. Depending on how bad it is, you can start by soaking it in a very soft solvent called evaporust. Evaporust is absolutely the best corrosion remover that I've ever run across and usually only requires about an hour or 2 of soaking. Once it's been soaked, or if the corrosion is minor, you can insert the wheel into a piece of pith wood and then you just use a sharpened toothpick along with polishing rouge or diamond paste to polish in between the leaves. This is going to take a while if you're doing it by hand, so the preferred method would be to remove the wheel from the pinion with your staking set and then use a rotary tool with a chisel edge silicone polishing wheel. Make sure to rinse off the parts very well before adding them to your final cleaning solutions because you don't want a bunch of polishing compound floating around in your cleaning liquids. The third part of your inspection is to inspect and polish the jewels. Start by pre-cleaning the jewels and shine a light under the jewel to make sure that none are broken or even cracked. If one is broken or cracked, it needs to be replaced, which will be the subject of another video on jeweling. If you're in this situation and you don't have a jeweling set, then just box it and move on to something else. Because with broken or cracked jewels, you're not going to be able to regulate the watch. Now, most people know about polishing or pegging out the jewel holes, so I'm not going to spend much time on this other than to say that if you're not doing it, you're probably losing a minimum of 5 to 10 degrees of amplitude, if not more. If you're working on an older 7-jewel movement, your train pivots are probably going to be worn so that they're out of round, and the watch will not be able to be regulated until that's repaired. Not only does out of round brass pivot holes create issues in the horizontal positions, but it turns the vertical positions into a complete disaster. That's also another video that we'll be doing on bushing. So if your movement has that issue, then box it up until you have the ability to rebush the pivot holes. Now, if you're working on a 7-jewel movement, if the pivots don't show signs of wear, then you polish the holes with a smoothing broach. Smoothing broaches have a very fine texture that will not only remove scratches in brass, but they also work harden the brass at the same time. Now, the fourth part of the train inspection is actually polishing the wheel pivots. The primary tool, which has been used for about 200 years, is called the Jacot tool. It is designed specifically for the precise repair and refinishing of very small wheel pivots. When searching for amplitude, the train wheel pivots are one of the major factors when it comes to power loss due to excessive friction. The pivots in these old movements have been running with little or no lubrication, leaving behind scratches, or even worse, changing the shape of the pivot itself. Since the jewels are a harder material than the steel pivots, any broken or cracked jewels will also wear scratches or grooves into the metal pivots. Pivots can also become pitted from corrosion or rust, all of which increase friction and reduce amplitude. The pivot lathe is used for correcting pivots with a burnisher and is not intended for grinding or polishing with gritty compounds. The burnisher you want to use is hardened steel. The runner beds are made of hard steel, and since sapphire is harder than steel, the sapphire will gradually wear down the surface of the steel runners, damaging them forever. The Jacot lathe serves a couple purposes. The first purpose is to remove minor grooves, tapering, and imperfections from the pivot. This is done with an extremely fine file. The file on the left is a number 6 cut, which is already extremely fine. And the one on the right is from the burnisher. Now, I don't know for sure, but I believe this is a number 10 cut, as it's quite finer than the number 6. This file can be used to reduce the size of a pivot on a replacement wheel where the jewel has been replaced with a smaller diameter hole from a previous repair, or you need to remove grooves that have been cut into the pivot. If you look at the cross section of a scratch under high magnification, you'll notice that on either side of the scratch, there are high spots where the material has been moved out of the scratch. When you look at a top section of a scratch, you'll notice that there's material moved out that is on both sides of the scratch. These are the high spots on the pivot and are the main thing that causes the additional friction. Burnishing is only accomplished by applying both pressure and friction, and the heat caused from that friction rolls over the high areas from both sides of the scratch and move it back into the low spots of the scratch. This process is known as metal displacement, and it helps to fill in surface scratches and imperfections, resulting in a more uniform and polished surface. This is also the exact same concept that's used when watch cases are buffed to remove scratches and gouges instead of sanding away material. Except in that case, you're using a hard felt wheel and polishing compound. Burnishing also work hardens the metal. As the metal is burnished, the pressure and friction rearrange the metal's crystal structure, making it denser and more resistant to future wear. The action of the burnisher will slightly reduce the diameter of the pivot because some of the displaced metal that are on the edges of the scratch is lost, but it's such a small amount that it will not affect the side shape. Now, there are lots of different models of Jacot lathes, and they all work on a similar principle. The only recommendation I would give you is to stay away from the earliest models. The first lathes that were produced have a lot more small components that can become lost when you're buying such an old tool, and it's very difficult to tell if the set is complete. Let's take a look at the one I use, which is pretty typical of what you should be looking for. The bed is the main structure of the lathe, and like other lathes, it consists of a head and tailstock along with 2 locking nuts. The headstock houses the dead center spindle of the lathe, and this is where the pivot you're not polishing is held in place by friction. The spindle will have 2 different sized tapered holes, one on each end of the spindle. A complete Jacot lathe will have at least 2 of these spindles, giving you 4 hole sizes, which can accommodate any pivot size. The drum rotates on the dead center spindle. It is driven back and forth by the bow, which fits into the drum pulley slot. Attached to the end of the drum is the carrier or drive pin, which fits on either side of the wheel spokes. And as the drum is rotated, the carrier pushes on the spoke back and forth, turning the wheel. Now, some lathes come with single drive pins, but I feel they're a little harder on the spokes of brass wheels as it's moving back and forth, so it's probably something I would stay away from if possible. Below the dead center spindle is the carrier adjuster. The disc on the end fits into the large groove on the back of the drum and screws in and out to fine-tune the carrier's position inside the wheel spokes. This helps to position the carrier so that it can turn the spokes without poking through the other side of the wheel, getting in the way of the burnisher. The tailstock is machined to support the pivot runner. The pivot runner is faceted on the end with a flat surface pointing up, which is meant to provide support for the burnisher. In the center of the facet are beds machined to an exact depth that support the pivot that's being polished. The depth of the beds are marked on the pivot runner and are shown in 1/100ths of a millimeter. And that number represents the distance from the bottom to the top of the bed. When the pivot runner is inserted into the tailstock, the guide bar locks the orientation of the runner into the lathe by sliding into the groove on the runner hub. Once the wheel has been positioned in the spindle and the other pivot is sitting in the hub on the pivot runner, everything is locked into place with the 2 locking nuts. The wheel is not actually locked into the lathe, but is held in place by the burnisher resting on top of it. Now, traditionally, Jacot lathes are powered by a bow. If you're lucky, yours will come with the original bow, but sometimes they only come with a cord, like mine did. I made this bow by taking the spline out of an old umbrella and attaching the string to it, and it works perfectly fine. Today, my preferred method is to use a retractable ID card holder. All I do is use a piece of double-sided tape and stick it to my workbench, making sure that the string is in line with the groove on the drum. Otherwise, it tends to come out and knock the wheel out of place. The correct way to wrap the string around the pulley is to go underneath the drum first and then wrap around the drum, pulling from the opposite side so that the top of the pulley will be turning toward you as the bow or string is pulled. The bow or string is pulled as the burnisher is pushed and vice versa. The burnisher is very important to the success in smoothing pivots. They are available in either a left or right-handed configuration and usually come with the burnisher on one end and a file on the other. Now, when you look at the burnisher, you'll notice that one end has a tapered sharp angle and the opposite edge of the burnisher has a slightly rounded angle. The sharp angled edge ensures that the burnisher can get tight to the shoulder of the pivot. And the rounded edge is used when you're polishing conical shaped pivots, like on a balance staff. Ordering burnishers can be a little bit confusing when you first look at them, but just remember that you want a right-handed burnisher when the pivot being burnished is on the right side of the burnisher. And you want a left-handed burnisher when the pivot that you're going to be working on is on the left side of the burnisher. I'm right-handed, so I use a left-handed burnisher. Now, the burnisher itself is also a file, but not in the traditional sense. When you run your fingernail across it, you feel a very slight texture. The burnisher actually has lines that run perpendicular to the length of the steel, which makes these lines parallel to the pivot. It is these faint lines that are rolling back and forth across the pivot, which is actually stretching out the high spots and filling in the scratches. Now, in order for the burnisher to do this, the steel must have fine enough lines scratched on it to be able to grab and stretch the steel, but not so much so that the high spots are actually knocked off. If this happens, the burnishing process can get very long. Now, I've probably seen a dozen new burnishers over the years, and none of them have been in what I would consider usable condition. Typically, what you'll find on a new burnisher is that they're much too aggressive for good polishing. On top of that, depending on how much you use the burnisher, you're going to need to redress the steel. So let me show you quickly how I do that. I start with a very flat sharpening stone. The one I use is equal to 1,000 grit. I add a lubricating oil to the stone, and holding the burnisher flat, I draw the burnisher towards me and to the side while adding steady pressure to ensure that it stays flat on the stone. Now, once all the ridges have been removed from the steel and it's flat again, I use a piece of 400 grit wet dry sandpaper. I cut a strip and I fold it over and tuck it under my sharpening stone. I then add my lubricating oil to the sandpaper, and again, holding the burnisher down flat with pressure, I pull the burnisher straight back towards me. I'll do this for a minute or so and then wipe it down and check my progress. And I keep doing it until I'm happy that the lines that I've cut into the steel are good enough. Now, it's a little hard to describe exactly what I'm looking for, but I use the fingernail test, and basically you want to feel that the lines are now closer together and smaller. I would describe the feeling that I'm looking for kind of like the difference in opening up a small zipper and how that feels, and then opening up a larger zipper. You can really feel the difference of the lines that are smaller and closer together. Now, just as a side note, there's nothing that you really need to do to prep the other side where the file is, other than keeping it clean and lubricating it with a light coat of oil. And while we're talking about oil, there's only two requirements needed in your lubrication. It should be able to draw the metal particulates, the ones that are actually lost from around the scratches as you're burnishing, and draw them away from the pivot as you're burnishing it. If it doesn't draw them away, the metal dust will collect where the burnisher meets the surface of the steel. Now, depending on how much it is, this can cause the particulates to become somewhat of an abrasive, which will prevent you from getting a really smooth surface. The second requirement is that it shouldn't evaporate when it starts getting hot. This burnishing process will generate a small amount of heat at the point where the burnisher meets the pivot. If the lubricant evaporates under the heat, it'll be the same as if no oil was used at all. I learned burnishing using an oil called Hops No. 9 gun lubrication oil. And I've been using it ever since, and I've never seen a reason to change. It works awesome. Now, when using the Jacot tool, it's very important to select the proper size bed for the pivot being burnished. If the bed is too large for the pivot will not stand up high enough for the burnisher to touch it. But on the other hand, if the bed is too small for the pivot will stand up too high above the bed, and the burnisher is likely to taper the pivot. This shows a pivot resting in a bed which is too small for the pivot. The pivot is standing up too high above the surface of the runner, which will cause the pivot to become tapered when it's burnished. Now, if you're actually trying to reduce a pivot a lot, it would be way better to remove the material in small steps by using progressively smaller pivot beds until the proper size and finish is achieved. So start by measuring the pivot to get its current size. I use a digital micrometer by Matoya, which is extremely accurate, especially for the low price. In our example, the pivot measures 79 hundredths of a millimeter. So I need to use the next smallest bed, which is 75 hundredths of a millimeter. That's going to leave 4 hundredths of a millimeter above the bed. One of the other reasons I like to use a micrometer is that you can see whether or not the pivot actually has been tapered. If there actually is a taper, then you'll need to use the file on the other side first to reduce the pivot before it can be burnished. So here's what we're going for. The pivot should have a minimum of 1/100th of a millimeter above the surface and no more than 5/100th of a millimeter above the surface. Now, when setting up a pinion or arbor in the Jacot lathe, there needs to be a small space between the shoulder of the pivot and the end of the runner to allow for freedom of movement. This also keeps the end of the runner from scratching the shoulder of the pivot, which just creates another friction point. Now, while I go through and burnish the train wheels, I have a new segment that I'm going to start doing and adding it into some of my videos. I have a lot of people that contact me about the successes they've been having from studying my videos and applying what they're learning. So I want to start featuring some of these completed projects that people are extra proud of. Our first viewer project is going to be a pocket watch by a member of our community named Steve. This is a beautiful Watchmaking model, 1908, grade 610, that was produced right around 1932. It's a typical size 16 pocket watch that must have been very popular back in the day because Waltham produced about 600,000 of them. But what's amazing about this is, other than the fact that it's got a very clean dial, is the results that he got from this movement that only has 7 jewels. Now, Steve told me that when he got it, it was missing an impulse jewel, it had a bad mainspring, and that the second wheel had almost no side or end shake. What probably happened is someone tried to service it and probably the second wheel was broken and they put a new one in and it was just too tight and they didn't know what to do. So what Steve did is he used a smoothing broach and he opened up the pivot holes just enough to give the proper side and end shake, kind of like what we was talking about earlier. Then to replace the impulse jewel, he disassembled the balance and was able to replace the impulse jewel so perfectly that when you look at the trace lines on his time grapher, the readings look very clean. And if that's your first impulse jewel, Steve, I'm pretty impressed. The other thing that's really impressive is that he was able to get the 270 degrees in the dial up position and 274 degrees dial down, and still have a great beat error under 0.4 milliseconds. Now, I would love to see the horizontal positions a little closer together. But guys, this is a 7-jewel movement that's over 90 years old. So there's really no need for any criticism on what he did at all. So Steve, brother, all I can say is well done. I'm glad you're part of the community. I'm glad I was able to help. Keep them coming, man. So if you guys have a project that you've worked on that you're extra proud of, send Pictures and as much information about the movement and what you did to me at the email in the About Me section, and I'll include it in a video. Now, if you're one of my regular viewers, you know that it's taken me a little bit longer to get videos out than it was before. And there's two reasons for that. One, they're getting a lot more complicated and they just take more time to write, film, and edit. But the main reason is that I am in the process of writing a complete 2-year watchmaking course. This course is going to include in detail everything that you need to know to become a watchmaker. From using the tools to servicing, inspecting, troubleshooting, watch adjustment, and regulation. It's also going to include how to work and troubleshoot chronographs, as well as all types of repairs, not only to the movement, but to the case as well. Now, the course will be in a written format with short and long form videos to back up and go into maybe a little bit more detail or demonstration of what we're talking about. This has taken a lot of careful planning, and a lot of it is going to be based on my 35 years as a watchmaker, and it's just going to have a ton of information. Now, the first lessons will be going up on my website in about a month or so. And all this work has really been made possible by the support of all my patrons. Now, once the first years of content has been posted on the website, then I'm going to open it up to yearly subscriptions. But for my top 2-tier patrons, you'll be getting access as part of your Patreon benefits as soon as items are uploaded. I'll have a lot more information as we get closer to the launch. So now that we've got all the pivots burnished, I'm going to reinstall the train, get it lubricated, and we're going to let it run for 24 hours. And then let's look at the time grapher from where we last left off. So when you look at our last time grapher reading on the left, you can see we had a maximum of 205 degrees of amplitude after making some slight adjustments to the barrel in the last video. On the right side will be our current results. I started by re-inspecting the teeth and pinion leaves in the train. I checked the end and side shake of the 4 wheels. So when you look at our last time grapher reading on the left, you can see we had a maximum of 205 degrees of amplitude after making some slight adjustments to the barrel in the last video. On the right side will be our current results. I started by re-inspecting the teeth and pinion leaves in the train. I checked the end and side shake of the 4 wheels. I inspected to make sure we didn't have any broken or cracked jewels. I pegged out the jewel holes, and then I spent about 30 minutes polishing the 4 wheels of the train on the Jacot lathe. If we had done that during the original disassembly, along with the work that we did in the last video on the mainspring barrel, it's reasonable to assume that we would have had this amplitude the first time we installed the balance wheel. But since we didn't do these things, now we have to go back looking for amplitude. And that's the whole purpose of this video series. You see, in watchmaking, everything matters. If you just didn't know, now you do. And if you're new to working on these old pocket watches, skipping these steps is going to greatly affect what you can expect out of these movements. Now, looking at our results, we can see in the horizontal positions that dial up is hitting 245 degrees, which means that the amplitude is there, but something's holding it back in the dial down position. We picked up an additional 40 degrees from basically pegging the jewels and polishing the pivots. Now we're going to turn our attention to increasing amplitude in the escapement, and we're going to bring those 2 horizontal positions together. We're only about 25 degrees away from our goal of 270 degrees. Once I have the amplitude I need, then we're going to regulate the movement and case it up into a wristwatch. So thanks for watching. Let me know if you have any questions, and we'll see you in the next video.